Hello and welcome to Zetec's webinar on improving austenitic weld inspections in upstream, midstream, downstream, and petrochemical sectors. My name is Wayne Waxman. I'm the Director of Marketing at Zetec. I'd like to thank everyone for joining us today. I have a couple of logistical items before we get started. Everyone is in listen-only mode, and we are recording today's session, so you can review and listen to it or share with your colleagues in your organization. Everyone who registered for this webinar will receive an email later this week with a link to the recording. Please note, the audio or sound for this webinar will only play through computer speakers and not over the phone. Please view and listen to this webinar through your computer. Finally, there will be a Q&A session at the end of this webinar where we will be answering your questions. You don't need to wait until the end of the webinar to send us a question. If a question comes to mind at any time, just type it in the questions section on your GoToWebinar panel. Before I turn this over to our presenter, I would like to give a quick overview of Zetec. Zetec is a global NDT leader. For nearly 50 years, we've advanced the science and standards in both ultrasonic and eddy current technologies, setting new heights in inspection performance, productivity, and predictability. Zetec's proven expertise and complete product portfolio serve the inspection needs of our customers worldwide in transportation, power generation, manufacturing, and oil and gas. Zetec is a subsidiary of Roper Technologies. Let's get to today's presentation. I'd like to introduce Guy Maas with Zetec. Guy has been involved in advanced UT method development and implementation, capability assessment, and software development for more than 25 years. Since 2000, he has held various positions at Zetec and RDTech, including Sales Director, Product Manager, and UT Applications Manager. Guy is currently the Sales Engineer Director, UT, at Zetec. With that, I'd now like to turn this webinar over to Guy.
Thanks, Wayne. Hello, I'm Guy Maas, and I have the pleasure of presenting our solutions for improving austenitic steel weld inspection in various sectors of the oil and gas industry. This is the agenda of our webinar today. First, I will give a short introduction about austenitic materials and an overview of typical austenitic weld configurations that are encountered in the oil and gas industry. After that, I will address the specific challenges presented by austenitic steel welds when performing phased array UT examinations. Then, I will present the key components of our solution for efficient and reliable inspection of austenitic welds, including recent hardware and software product innovation at Zetec. A large part of this webinar will be used to illustrate good practice in setting up and deploying inspection techniques for different austenitic weld configurations and flaw types. I will also show examination data on representative weld specimens and discuss the results. Throughout this part of the webinar, I will demonstrate the capability and the efficiency of the onboard Ultravision Touch software for setting up the inspection techniques and for data analysis. And then finally, we will wrap up with some conclusions and take your questions. Let's have a look at some austenitic materials that are typically used in pressure retaining welds. Austenitic stainless steels contain a minimum of 16% chromium and sufficient nickel and/or manganese to retain an austenitic structure at all temperatures from the cryogenic region to the melting point of the alloy. They have an austenitic crystalline structure, which is a face-centered cubic structure. This makes the steel less brittle at low temperatures and essentially non-magnetic. The most widely used austenite steel is 304, containing 18% chromium and 8% nickel. The major benefit of austenitic stainless steels is their high corrosion resistance compared to regular carbon steel. Duplex stainless steels have a mixed microstructure of austenite and ferrite, typically a 50-50 mix. Duplex has roughly twice the strength compared to an austenitic stainless steel and has improved resistance to pitting corrosion and stress corrosion cracking. The properties of Duplex are achieved with an overall lower alloy content than similar performing austenitic grades, which makes them cost-effective for many applications. Inconel is another family of austenitic superalloys containing over 50% nickel and over 15% chromium, in addition to other elements. These materials are oxidation corrosion resistant and well suited for service in extreme environments in terms of pressure and heat. Inconel retains its strength over a wide temperature range and is therefore attractive for high temperature applications. So let us look in more detail at the use of these austenitic materials in the oil and gas industry, starting with the upstream segment. From surface mining in the Canadian oil sands to downhole exploration and practically every setting in between, high alloy austenite materials are being used by oil producers and contractors to protect against highly abrasive and corrosive upstream conditions. In topside construction, the incoming mixture of oil, gas, and sand in the main process piping requires resistance to seawater, erosion, hydrogen sulfides, and carbon dioxide. The addition of high temperatures, high pressure, and highly corrosive fluids requires the use of high-grade austenitic materials. In subsea wellhead equipment and Christmas trees, duplex materials are used because they are less sensitive to stress corrosion cracking. For transportation activities in midstream, the use of duplex-grade steels for storage tanks allows up to 40% wall thickness reduction at equal strength, thus creating saving in welding material, transportation, and construction costs. Corrosion-resistant alloys, or CRAs, are used to clad the inside surface of steel pipe, and 9% nickel alloys are typically used for LNG tank manufacturing. And finally, in the downstream segment and in petrochemical plants, the great variation of requirements for different processes in the refining industry leads to a wider use of materials with broader tolerances to pressure, temperature, and acidity. For a long time, industrial radiography has been the commonly used examination technique after welding, but this technology has several drawbacks. RT is insensitive to some misoriented planar defects. It does not provide immediate feedback to the welders, and it is disruptive to other construction activities. Due to more stringent regulations on the use of RT, the oil and gas industry shows increased interest in phased array UT as alternative volumetric inspection technique, even for austenitic welds. After this introduction, let us now dive into the specific challenges presented by austenitic steel welds when performing ultrasonic examinations. As opposed to regular carbon steel, these materials are anisotropic, which means that the physical characteristics of the material depend on the orientation of the crystal. In practice, for UT examinations, this means that the wave velocity and the attenuation will depend on the relative angle between the acoustic beam and the crystal. Austenitic materials have a much coarser grain structure than carbon steel. Individual grains can be as large as several millimeters. And it is important to mention that this is larger than the wavelength of the acoustic beams that are commonly used in NDT. Also, different grain structures can exist in base material and weld material, depending on the cooling and welding processes. The anisotropic coarse-grained structure of stainless steel and dissimilar metal welds typically results in a strange behavior of the ultrasonic beam when propagating through the material. This finally results in very challenging conditions for phased array UT inspections. For example, the attenuation of the sound beam is high and variable. Also, we will typically see a high noise level because each of the large grains will act as a reflector for the sound wave. Then there is the low-pass filter effect. This means that the austenitic material will put a limit on the frequencies that can effectively propagate through it. This will drive us to use lower frequency probes. The ultrasonic beams will change direction and will be distorted by the individual large grains. And finally, as if the previous challenges were not enough, all phenomena will vary depending on the location of the phased array probe along the weld. The ray tracing images on the right side of this slide were generated in the 80s by physicists of the UK Atomic Energy Agency and compare the behavior of longitudinal waves and vertically polarized shear waves when propagating through a dendritic austenitic weld structure. We can see that the L wave beam somehow changes direction, but it will effectively propagate through the weld. On the contrary, the shear wave beam literally plunges into the weld root and will therefore not detect flaws on the far side of the weld. Of course, this is only one configuration, but it clearly illustrates the challenges that we are facing when inspecting austenitic welds. It also shows that we need to drastically adapt our inspection techniques to be successful in these configurations. Now that we have identified the challenges, let's look at the proposed solution. In fact, most of the elements of a successful inspection solution for austenitic welds are known to UT experts. Phased array UT examinations techniques for stainless steel and dissimilar metal welds have been qualified and applied for in-service inspection in nuclear power plants since more than 10 years. These techniques include low-frequency 2D matrix array probes to generate both L waves and shear wave beams for complete weld coverage. We will take a deeper dive into the benefits of these probe assemblies in the next slides. Unfortunately, until recently, the field implementation of these techniques was perceived as complex and expensive because it required high-end equipment and software, or multiple software packages. Last year, Zetec launched its Topaz 32 portable phased array unit controlled by the Ultravision Touch software with onboard support of 2D matrix arrays. We will demonstrate in this webinar that this innovation allows for the efficient field deployment of robust inspection procedures using either automated or encoded manually driven scanners. Examination procedures for austenitic steel welds typically include low-frequency dual matrix array probes, often called DMA probes, with frequencies from 1.5 to 3.5 MHz. The dual transmit-receive configuration offers the following benefits. First of all, there is no near-surface dead zone. Also, there are no ghost echoes caused by internal reflections in the wedge. This means that the wedges don't require any dampening material on the front, so they can be made shorter. And as a result, the exit point of the probe can be positioned closer to the weld. This will allow for better coverage in the first half skip. But most of all, the convolution or overlapping of the transmitter and receiver beams results in a better sensitivity and signal-to-noise ratio. And let us constantly keep in mind that shear waves can be used for examination of fine-grained base material, but L-waves will provide better inspection capability for propagation through the coarse-grain austenitic weld material. All the benefits mentioned in my previous slide are also true for conventional transmit-receive probes, and this good practice has been known and applied by several probe manufacturers and NDE service companies as far back as 1980. But phase array UT, and more specific 2D matrix array technology, enables a number of additional benefits. First of all, well-designed DMA probes allow for adequate beam steering to provide full coverage of the examination volume on the first half skip. Also, they can be controlled to focus at various depths and can therefore be used for a wider range of weld thicknesses. The acoustic beam simulations on this slide, performed with the Ultravision Classic software, clearly illustrate these concepts. An additional benefit of dual matrix array probes is that they can be used for simultaneous variation of the refracted angle and the skew angle of the probe. This can be used to improve the detection capability on misoriented flaws and also for increasing the inspection coverage. The acoustic beam simulations on this slide show beams at 40-degree L waves generated with no skew and with 15-degree skew. We can observe that the shape and the intensity of the beams are very similar. Based on long time experience and supported by acoustic beam simulation work, Zetec has designed a set of standard DMA probes. The frequency and the active surface of each probe are optimized for a given material attenuation and wall thickness range. Two probe heads are attached to a single Z-Pack connector to simplify field deployment. The element configuration in each design was selected for maximum steering capability without any relevant side lobes. We also offer exchangeable wedge assemblies with minimal footprint in the incidence plane and contoured to match the pipe OD. The wedges include carbine pins and irrigation points, and they are compatible with various Zetec and third-party scanners. So for a majority of common austenitic weld inspections, our customers can now benefit from Zetec's know-how and select the most suitable standard DMA probe for their configuration at hand. Of course, for very thick or very attenuating austenitic material, or for special geometries, we may need to design custom 2D matrix array assemblies. As previously mentioned, the Topaz 32 phase array unit, controlled by the Ultravision Touch advanced software, is key to the efficiency of our solution. Topaz 32 is a high-performance portable unit with a 32-128 PR configuration. It is battery-operated, very rugged, and has no air intake. All this facilitates field deployment in harsh conditions. The Topaz 32 has a 64-bit onboard computer that allows for fast processing. The onboard Ultravision Touch software fully supports a wide range of 2D matrix array configurations. No additional software package is required. In addition, guided setup of inspection techniques is available for the Zetec standard DMA probes that we have just discussed. The Ultravision Touch software offers visual feedback on focal loss, which is quite important when using 2D arrays. Accurate and online imaging of inspection data is available, not only the raw A-scan and sector scan views, but also the dynamic volumetric merge views. Topaz 32 has the capability to record large data files, up to 2 gigabytes. and it includes all the required software tools for efficient and reliable analysis of inspection data on plate and pipe welds. And finally, the Topaz 32 supports encoded, two-sided austenitic weld inspection with DMA probes when combined with its dedicated splitter box. Before looking into specific weld configurations, I would like to review a few generic keystones of good practice in relation with austenitic weld inspection. And by the way, all this is also useful for advanced carbon steel weld inspections. First of all, reliable ultrasonic examination of austenitic welds requires careful design of inspection techniques and the use of state-of-the-art probes. The probe frequency, the wave mode, L waves or shear waves, the active aperture, and the beam focusing are to be selected, taking into account the base materials, the weld type and the weld material, and finally the thickness and the geometry of the component. Acoustic beam simulation is an essential tool to design probe and wedge assemblies and to perform preliminary assessment of the inspection capability. But still, experimental validation of detection and sizing capability on representative test specimens is highly recommended for a successful inspection. And finally, encoded examinations with offline data analysis are to be preferred for more challenging inspection configurations. Let's start with a frequently encountered configuration: homogeneous stainless steel plate and pipe welds with the weld cap in place. Manufacturing inspections of stainless steel and corrosion-resistant alloy or CRA welds in lieu of RT require coverage of the complete wall thickness of the weld volume and the heat-affected zone. In carbon steel welds, shear wave beams are used to insonify the examination volume after skip. For CRA welds, this technique is not reliable because of the poor reflection on the clad ID surface, and also because of the poor propagation in the austenitic alloy weld volume. For homogeneous stainless steel welds, the shear wave beams can be used for base material examination only. We will show how to set up an alternative solution for the detection and sizing of circumferential flaws using a Zetec standard DMA probe at 2.25 MHz with refracted L-wave angles from 30 to 85 degrees for full coverage of the examination volume without skip. The first test specimen is a 304 stainless steel plate weld with a wall thickness of 1 inch. The weld has a typical V-bevel and an as-welded surface condition. It contains 4 realistic and well-documented welding defects oriented parallel to the weld: a lack of fusion, an incomplete penetration, a toe crack, and a cluster of porosities. We will now demonstrate how the Ultravision Touch software guides the operator through an efficient workflow for preparing the weld inspection setup. First, the weld geometry needs to be defined. The material, the plate thickness, the V-bevel, and the parameters for the weld cap and heat-affected zone can be easily configured in the graphical user interface of the Topaz 32. Once the specimen is completely defined, the operator could select a probe from the database or create a new probe from scratch. But when using a Zetec standard DMA probe with the Topaz 32, the setup process becomes even simpler. Based on the geometry of the weld, the proposed setup feature of Ultravision Touch will offer a list of inspection techniques, combining appropriate probes and wedges. As soon as the operator selects an inspection technique, the software will show a more detailed description, and when the operator accepts and confirms his agreement with the proposed configuration, the probe, the wedge, and the basic UT parameters will be automatically set to values that allow for optimum detection capability and complete coverage of the examination volume. The content of the proposed setup feature can be overruled by the operator, and it can also be permanently modified to comply with specific company work instructions. The graphical user interface of the Ultravision Touch calculator allows to visualize the scan plan and coverage. The element configuration of the matrix arrays are unambiguously indicated in the top view image to facilitate verification by the operator. If necessary, the operator can easily adjust the position, the sweep, and the time-based parameters. The setup is now ready to be used. No additional software was required. Let us now review the inspection data from the stainless steel plate weld in the Ultravision Touch software. This screen layout shows the raw data from a one-line scan. We have the following views on the screen. On the right side, we see the weld cross-section on the sectorial view with the weld bevel overlay. Top left, we have the weld side view showing the indication depth and the position along the weld. And down left, the A-scan signal linked to the data cursor. By moving the data cursor and the angle cursor, we can scroll through the data. But detailed analysis on raw data is often a time-consuming and laborious process, especially in the case of austenitic welds due to the presence of mode-converted signals. The volumetric merge tool allows us to drastically speed up the process, while maintaining the reliability and the precision of the analysis. By selecting a previously created screen layout, the operator can rapidly switch to the merged data. The layout is organized in a similar way as the raw data, except that the A-scan view has been replaced by the top view. We are now looking at the merged data from all refracted angles from 30 to 85 degrees L waves for the whole weld length. Data acquisition was performed at low gain setting to avoid saturation on flaws with high reflectivity. The 16-bit data resolution allows us to use appropriate soft gain settings for each defect type. The projection gates can be positioned to facilitate data interpretation, for instance, by hiding the strong root signal on the top view and by eliminating the shear wave mode conversions on the side view. Still using the projection gates, the analyst can easily isolate and visualize every individual indication at different locations along the weld. On this slide, you can see the end view images from the individual flaws, generated with the same merged data group. The lack of fusion defect on the near side of the weld is clearly detected even through non-specular reflections on the upper and lower edge. An incomplete penetration defect, 1.5 mm high, is easily detected and discriminated from the regular root echo. In fact, the low refracted angles also provide good detection capability on ID cracks on both sides of the weld. Tip signals can be resolved for accurate sizing of small cracks from the near side of the weld. The high-angle L-wave beams provide excellent detection of a near-surface crack called toe crack without any noise from the side lobe signals. A cluster of porosity in the center of the weld material can be well detected and demonstrates the propagation capability of the longitudinal wave beams through weld material. In this case, all flaws could be detected from one side of the weld with refracted L waves generated by the standard 2.25 MHz DMA probe. Our second test case is a 304 stainless steel pipe weld, 24 inches in diameter and with a wall thickness of 1.35 inch or 35 millimeters. The weld has a double V-bevel and the weld cap is in place. We will use a large circumferential ID crack in the heat-affected zone of this weld to illustrate the difference in detection capability between the commonly used shear wave inspection techniques and the DMA probes generating L waves. Let's look at shear wave examination data first. This slide shows merged data from 40 to 70 degree beams obtained with the standard Zetec AM 2.25 MHz probe in pulse echo mode. The crack is on the near side of the weld, so the acoustic beam is passing through relatively fine-grained base material, and we get a clear detection of the crack with potentially very accurate length sizing. We cannot observe any clear tip signals for through-wall sizing. This next slide shows merged data obtained with the same 2.25 MHz probe, but with the crack on the far side of the weld. In this configuration, the acoustic beam needs to propagate through the austenitic weld, and the large crack is by no means detected. Increasing the soft gain will only increase the amplitude of the grain noise. The flaw signals are just not there. Then let's take a look at the L wave examination data. This slide shows merged data from 30 to 85 degrees obtained with the Zetec DMA probe at 2.25 MHz in TRL mode. The crack is on the near side of the weld, and the image from the L wave beam clearly shows a corner trap signal and very well resolved tip signals. The ID crack is very well detected. The signal to noise ratio was measured at 17 dBs. Let's use this example to discuss the sizing procedure for ID cracks in austenitic steel. We will use the large and high amplitude corner trap indication to determine the length of the crack. When inspecting carbon steel components and welds, the 6 dB amplitude drop technique is most commonly used and provides fairly accurate results for length sizing. On the contrary, when using DMA probes in stainless steel welds, it was empirically demonstrated that the 6 dB drop technique has a strong tendency for undersizing the length of the flaw. The 12 dB drop, or even the full amplitude drop, provide more accurate results. Full amplitude drop means that we follow the response of the flaw down to the acoustic noise level. In this case, we have compared the 6 dB drop and the 12 dB drop techniques. The 6 dB drop sizing result was 26 millimeters, and the 12 dB drop technique found a flaw length of 37 millimeters, compared to the actual length of 34 millimeters. The result of the 12 dB drop technique is to be preferred because it is more accurate and, in addition, a conservative assessment of the crack. The tip diffraction technique is known to provide the most accurate through-wall sizing results on cracks. The reference cursor is positioned at the center of the corner trap, and then the operator needs to examine the signals above the ID surface in more detail. Tip diffraction signals typically have much lower amplitude than the corner traps, so we need to apply some soft gain. As we do that, we can see several parts of the crack edge lightening up. As shown on the slide, the center of the highest clearly resolved signal should be taken into account for through-wall measurement. This is where the measurement cursor is positioned, and now the crack depth can be read from the information views. And finally, let's look at the L wave examination from the other side of the weld. The crack is now on the far side and can still be clearly detected by adequately positioning the projection gates. This proves that the L-wave beam has propagated through the weld without too much attenuation or distortion. For this large crack, the signal-to-noise ratio was actually very similar to the result from the near-side examination, but it might be reduced for smaller ID cracks. This example clearly shows that the L-wave beams generated by well-designed DMA probes can reliably detect flaws through austenitic weld material. In this specific case, the data even allow for reliable length sizing. So if an austenitic weld configuration with single-side access needs to be inspected, L-waves drastically improve the quality of the examination. We do have to be aware, though, that true wall sizing for far side flaws is often very challenging due to weak and not well resolved tip signals. If the weld cannot be removed prior to the UT examination, no probe can be positioned on the weld. Therefore, the detection of actual flaws, and specifically IGSEC near to the ID surface, can be quite challenging. In such cases, single matrix array probes in pulse echo mode can be used to skew the sound beam under the weld cap. Since the sound beam essentially propagates in base material, shear waves can reliably detect flaws at the near side of the weld. As indicated on the images on this slide, the operator should not rely on signals that seem to originate from the far side of the weld. Ideally, the weld should be inspected with 4 beam orientations, so 2 symmetrical wedge assemblies are required to examine from opposite directions, clockwise and counterclockwise. Let us look how the onboard Ultravision Touch calculator handles the definition of focal law groups with various refracted angles and skew angles. The specimen has already been defined. It is a 20-inch diameter stainless steel pipe weld with a wall thickness of roughly 1 inch or 25 millimeters. In this example, we are using one of the standard Zetec matrix arrays at 1.5 MHz, but this time in a pulse echo configuration. We can load the probe parameters from the database. A custom wedge was designed with appropriate wedge and roof angles for detection of actual ID cracks in the considered weld configuration. The wedge parameters are also loaded from the database. After selecting the probe and the wedge, the onboard calculator allows the operator to select the nominal skew, the ranges, and the resolution of both refracted and skew angles, and the focusing depth. Depending on the frequency and the size of the individual elements of the array, the probe assembly can generate shear wave beams with refracted angles between 40 and 65 degrees, and skew angles between 20 and 50 degrees relative to the scan axis orientation. Typically, more than 50 acoustic beams are fired at each probe position. The visual feedback of the calculator is very important. The ray tracing allows the operator to correctly position the probe relative to the weld for adequate coverage of the heat-affected zone on the near side of the weld. Upon calculating the focal laws, the Topaz 32 returns to setup mode, and the sector scan can be visualized together with the weld bevel overlay. This example illustrates how the onboard calculator supports even more complex inspection techniques with matrix arrays, without requiring any additional tools. My next slide shows the phase array images obtained with this probe configuration on an actual crack in the considered pipe weld. The images shown are merged data from all focal laws. On the right side of the slide, we can see the end view. It shows that the applied group of skewed focal laws in combination with a two-line inspection sequence allows to fully cover the examination volume on one side of the weld. The actual positions of the two scan lines are determined as a function of the pipe thickness and the weld crown width. The first scan line, as close as possible to the weld crown toe, aims for flaws located near to the weld root, and the second scan line completes the coverage of the heat-affected zone. The footprint of the probe is optimized to bring the beam exit point as close as possible to the weld crown toe without generating major internal reflections in the wedge. The different views, including the onboard polar view, show that the actual ID crack is accurately positioned in the heat-affected zone on the ID of the pipe. The crack was detected with various skew angles, and a high signal-to-noise ratio can be observed. This inspection technique was demonstrated to be quite effective for the detection of essentially axial cracks. Let's now move on to a different type of weld. Dissimilar metal, or DM welds, typically join two or more different materials and mostly involve Inconel alloys. These welds are often used to connect clad carbon steel vessels to stainless steel piping. Dissimilar metal welds are a very challenging configuration for UT examination due to the various propagation issues in austenitic structures, the presence of multiple acoustic interfaces, and the sometimes very complex geometry. If the weld crowns are ground flush, this allows for scanning of the probes on the weld surface. For detection and sizing of circumferential flaws, 1.5 MHz DMA assemblies with a large footprint can be used to generate focal laws at 45, 60, and 70-degree L waves with an adaptable primary aperture. This aperture is then electronically scanned in the axial direction to create a set of linear focal laws. As shown before, the Ultravision Touch advanced software allows the operator to simply select the required dual array probes and wedges from the database. The onboard calculator then allows to define the appropriate parameters of the focal law groups for linear scanning and gives direct visual feedback on the coverage provided by the three insonification angles as shown on the images of this slide. The ultrasonic beams are oriented perpendicular to the weld, and a multiple line inspection sequence is used to fully cover the examination volume. The actual positions of the different scan lines are determined as a function of the pipe thickness, the weld bevel, and the access restrictions of the component. This examination technique has been proven very effective for various types of circumferential defects. Let us review some representative data in the Ultravision Touch software. We are looking at the previously merged data group from the 45-degree L-wave linear scan on a 12-inch diameter dissimilar metal weld with several acoustic interfaces and a wall thickness of 30 millimeters. The screen layout is similar to the one we used before in this webinar. After using the projection gates to eliminate mode-converted echoes, we can clearly observe two indications near the ID of the weld. They are signals from two circumferential ID surface breaking cracks. A rapid evaluation of the signal-to-noise ratio shows around 10 dB, which is an excellent result for this type of welds. It proves that low-frequency L-wave beams can adequately propagate through the weld material and through various acoustic interfaces. Let's use the larger crack indication to illustrate the detailed sizing procedures for ID cracks. First, it is useful to zoom in on the region of the indication. We can see a large high-amplitude corner trap indication at the ID of the specimen and some smaller amplitude signals above that. We will use the corner trap to determine the length of the crack. And as mentioned in a previous example, we will use the 12 dB amplitude drop technique. The soft gain setting and the color palette editor are quick manual tools to conduct this sizing exercise. For well-resolved flaws in easier materials, the software also supports an automated length sizing process by simply positioning the cursors around the indication. For through-wall sizing, we will use the tip diffraction technique. The reference cursor is positioned at the center of the corner trap, and then we examine the signals above the ID surface. We will apply soft gain to see several facets of the crack lightening up. The center of the highest clearly resolved signal above the corner trap is taken into account for through-wall measurement. We position the measurement cursor, and the crack depth can be read from the information views. Obviously, the tip diffraction technique cannot always be used successfully. For very small cracks, the corner trap will obscure the close by and weaker diffraction signals. Ideally, an experimental validation exercise on a representative welded specimen with EDM notches should be used to determine the lower limit of the cracks that can be reliably sized. As such, the absence of a resolved tip signal can be a good indication for a very small crack. The indication table in Ultravision Touch allows to rapidly save all the quantitative information about the indication while minimizing human error. Since the weld cap is ground flush, phased array probes can be scanned on the weld surface to inspect for actual flaws. Again, DMA probes at 1.5 MHz are used, but in this case, the probe assemblies are designed for sectorial scanning using the complete aperture of the probe. Typically, 8x4 matrix arrays will be used. The wedge assemblies are designed to allow for the generation of L-wave beams with several refracted angles between 25 and 65 degrees, with adaptable increments, and skew angles from -20 to 20 degrees, with typical increments of 2.5 degrees. This results in a total of approximately 80 acoustic beams being fired at each search unit position. The images on this slide show the visual representation of this inspection technique in the calculator. For actual flaw examinations, the ultrasonic beams are oriented essentially parallel to the weld. A multiple line inspection sequence is used to fully cover the examination volume. The skewing of the beams is used to reduce the required number of scan lines, and therefore the total inspection time. 2 scans are performed, one with the beams aiming in the clockwise direction and one aiming counterclockwise. This examination method is very effective for detection and sizing of actual flaws in austenitic components when the weld cap is ground flush. This slide shows the data obtained on a 14-inch diameter dissimilar metal weld with a wall thickness of 1.2 inch. In this case, the merged data from all skew angles for a refracted angle of 25 degrees are shown. This gives a very comprehensive image of the 2 flaw indications. The L-wave beams provide excellent detection capability with a high signal-to-noise ratio, and the polar view shows accurate positioning of the flaws in the cylindrical geometry. From all the information and the various case studies presented in our webinar today, we can draw the following conclusions in relation with phased array UT examination of austenitic welds. First of all, we have seen that inspection techniques based on 2D matrix array probes provide improved inspection capability on both circumferential and actual flaws in stainless steel and dissimilar metal welds. Standardized DMA probes generating refracted L waves can effectively cover the complete examination volume for stainless steel welds with weld cap in place, and allow to detect both planar and volumetric welding defects during manufacturing inspections. Inspections with 2D matrix array probes can be efficiently set up, deployed, and interpreted using the fully integrated Topaz 32 phase array unit and the onboard Ultravision Touch software without the need of any additional software package. And finally, in addition to our best-in-class products, Zetec can provide industry-leading expertise for improving your austenitic weld inspections. This concludes the presentation part of the webinar. We will now take some time to answer a few questions that have been received since the start of our webinar.